On a reef in shallow tropical water, a patch of sand shifts, and what looked like empty seabed is suddenly an animal. A moment ago, its skin matched the grain and color of the sand so closely that even a careful eye passed over it. Now, provoked, that same patch of skin turns into a pulsing storm of contrasting stripes, rolling from head to tail in waves bright enough to be seen from meters away. Nothing about the animal's shape has changed. Only the image it is showing the world has. This is the law that governs a cuttlefish's life. It cannot outrun most of what wants to eat it. And it cannot outmuscle most of what it wants to eat. What it has instead is control over its own appearance, moment to moment, down to the smallest patch of skin. In water crowded with sharp-eyed predators and equally sharp-eyed prey, that control is not decoration. It is the entire survival strategy, built into the skin itself. A cuttlefish is not a fish at all, despite the name. It is a cephalopod, a soft-bodied mollusk related to squid and octopuses, built around a mantle, 8 arms, 2 longer feeding tentacles, and a body designed less for speed than for information. That distinction matters, because everything remarkable about this animal traces back to a nervous system built for exactly one purpose: deciding constantly what image its skin should display next. The skin itself is not painted. It is engineered. Thousands of tiny organs called chromatophores sit just beneath the surface, each one a small sac of pigment surrounded by muscles. When those muscles contract, the sac stretches wide and the color shows. When they relax, the sac shrinks and the color all but disappears. Each chromatophore is wired directly to the nervous system, which means the cuttlefish is not slowly secreting a new pigment the way a chameleon's skin gradually shifts. It is switching thousands of individual pixels on and off in patterns in under a second, the way a screen redraws an image frame by frame. Color alone would not be enough to disappear against a reef. Real camouflage has to match texture as well as tone. And this is where the cuttlefish's skin becomes stranger still. Beneath the chromatophores sit structures called papillae, small muscular bumps that the animal can raise or flatten at will, turning smooth skin into a rough, three-dimensional surface that mimics coral, rock, or weed. A cuttlefish lying against a textured reef does not just change color to match it. It reshapes the surface of its own body, lifting dozens of tiny peaks and ridges, until its skin reads, to a passing predator's eye. A stone rather than flesh, color and texture together are still not the whole picture. Beneath both layers sit 2 more kinds of skin cells that most descriptions of cuttlefish camouflage skip entirely. Iridophores are structures that reflect light directly, bending it to produce shifting blues, greens, and metallic sheens without using pigment at all. The same basic principle behind the shimmer on a soap bubble. Beneath those, leucophores scatter light broadly, giving the skin a base layer of white or pale reflectance that the colored layers above can be built on top of. A cuttlefish's final appearance is the sum of all 3 systems stacked together: pigment, reflected color, and scattered light, running simultaneously across the same patch of skin. Losing any one layer would leave a visibly incomplete disguise. There's a deeper problem hiding underneath all of this, one that makes the whole system more remarkable rather than less. Cuttlefish eyes, as far as researchers have been able to determine, do not see color the way many of the animals watching them do. Yet the patterns cuttlefish produce closely track the colors of their surroundings. How an animal that may not perceive color in the way we understand it can still assemble color-accurate camouflage is a genuine open question. One researchers are still working through rather than one with a settled answer. And it is worth resisting the urge to turn that mystery into false certainty in either direction. None of this skin control matters if the cuttlefish cannot use it under real pressure, so watch what happens when it hunts. Approaching a shrimp across open sand, it does not creep forward looking like a predator. It flattens its color into a muted mottled pattern that reads as background clutter. And it advances in short pauses timed to the shrimp's own movements, staying still exactly when the shrimp might notice motion. Some cuttlefish take this further, flashing a rippling, hypnotic pattern of light and dark bands across their skin in the final approach. A display thought to distract or momentarily overload the prey's visual system in the instant before the strike. Then the two long feeding tentacles shoot forward faster than the eye can easily track, seize the shrimp, and draw it back to the waiting arms. The disguise and the ambush are not separate behaviors. The same skin that hid the approach primed the kill. The same tools flip entirely when the threat runs the other way. A reef fish large enough to swallow a cuttlefish whole triggers a completely different program. Instead of matching the background, the cuttlefish can flare into a high-contrast display, dark bands strobing across pale skin. Sometimes paired with a sudden change in body posture that makes it look larger and more aggressive than it actually is. This is a bluff, not a weapon, an attempt to make removal costly enough that the predator hesitates or moves on. Both by the same chromatophores that were producing camouflage seconds earlier. When display fails and contact becomes unavoidable, the cuttlefish has one more layer of defense built into its body, a sac of dark ink. Expelled in a sudden cloud that fouls the water and confuses a predator's sense of exactly where its target went. Some cuttlefish shape that release into a rough copy of their own outline. A decoy blob left hanging in the water, while the real animal jets away in a different direction under cover of the same cloud. It is a last resort, not a first plan sprayed only once real escape by disguise or bluff has already failed. Camouflage and threat display both demand restraint or aggression, but reproduction demands something else again. Visibility aimed at exactly one viewer while staying invisible to everyone else nearby. Male cuttlefish competing for a female's attention can produce zebra-striped patterns down one side of the body, the side facing the female. While running a plain, camouflaged pattern on the opposite side, facing away where a rival male or a passing predator might be watching. Splitting the display this precisely. Left side broadcasting and right side silent is only possible because chromatophores are controlled independently across the body, rather than as one uniform switch. The same system that hides a hunting cuttlefish from prey lets a courting cuttlefish speak to one audience while staying quiet to another only centimeters away. This split-sided display is not just clever theater, it carries real consequences for which males successfully mate at all. A smaller or subordinate male crowded out of direct competition by a larger rival can use exactly this technique to slip past him, running a convincing female-like pattern on the side facing the dominant male while displaying true courtship coloring on the side facing the female herself. The dominant male, reading only the disguised side, may not challenge the intruder at all. It is deception aimed with the same precision as camouflage against a predator. Deployed here against a rival of the same species rather than a hunter from another one. And it shows that the skin's usefulness extends even into contests, where the audience is another cuttlefish reading the same signals it produces itself. This system, powerful as it is, has real limits, and those limits shape how a cuttlefish actually lives rather than undermining the ability itself. Producing and controlling this much skin activity draws on a disproportionately large share of the animal's nervous system. And the cuttlefish, under sustained stress or exhaustion, visibly loses precision in its patterning, the sharp edges and fine texture blurring into something cruder. The system also cannot compensate for every kind of danger. Chemical cues, vibration, and detection through senses that do not rely on sight at all can locate a cuttlefish no matter how well its skin performs. And no pattern is truly permanent camouflage against every predator in every light. Sharks and marine mammals that rely heavily on senses other than color vision are far less impressed by a display built primarily to fool eyes. What makes the cuttlefish worth returning to is not any single trick in that list. It is that hunting, hiding, threatening, and courting all run through the exact same physical system, reconfigured almost instantly for whichever problem the moment demands. A predator's approach, a rival's challenge, and a mate's attention are, to a cuttlefish's skin, simply different images waiting to be drawn. In a stretch of water where nearly everything depends on being seen correctly or not seen at all, the cuttlefish did not evolve one defense. It evolved a screen and learned to control every pixel on it. This ability is not something a cuttlefish grows into slowly over a long life. Most species live only a year or two. The hatchling, only centimeters long, already carries a working version of the full chromatophore system from the moment it emerges from its egg. Producing recognizable camouflage patterns almost immediately rather than learning them over months, the way many young animals learn adult behavior. There is very little time to practice. A cuttlefish that cannot camouflage effectively within days of hatching is a cuttlefish unlikely to reach adulthood at all. And that pressure has almost certainly shaped how much of this system arrives pre-built rather than learned through trial and error. Not every threat on the reef responds to a visual display, and this is where the cuttlefish's system shows its clearest boundary. A moray eel hunting, largely by smell and by sensing water movement through narrow reef crevices, is far less troubled by a perfect camouflage pattern than a fish relying primarily on sight would be. Against a threat like this, color and texture matching offer little protection. And a cuttlefish's best option is often not display at all, but retreat into a crevice too narrow for the eel to follow. Or a fast retreat under an ink cloud released purely to mask movement rather than to fool an eye. The same animal that can vanish against sand in front of a hawkfish can be located easily by an eel that never looks at it directly. A reminder that an entire system built around controlling appearance only works against predators that hunt by appearance in the first place.